Britain entered the Second World War with a secret weapon that couldn't fit where it mattered most. Along the English coast, a chain of enormous steel towers rose from the cliffs like industrial lighthouses, each one bristling with aerials the size of railway carriages. These were the radar stations of Chain Home, the world's first operational early warning system, and they could spot Luftwaffe bombers crossing the channel from 70 miles away. RAF commanders watched with grim satisfaction as the plots appeared on their screens, scrambling Spitfires and Hurricanes to meet the threat, but this marvel of science had one crippling weakness. It was bolted to the ground. Fighter pilots hunted in the dark with nothing but their eyes and the uncertain glow of searchlights sweeping below. A Hurricane cockpit measured barely 4 feet across. The instrument panel held altimeters, compasses, fuel gauges, and precious little else. RAF Tangmere's night fighter crews would patrol for hours above the Sussex countryside, listening on crackling radios as ground controllers tried to talk them onto targets they could never see. The Luftwaffe knew this. German bomber streams exploited British blindness, arriving after sunset to pound docks, factories, and homes, whilst Fighter Command groped uselessly through the blackness. During the winter of 1939, kill rates after dark dropped below 1 aircraft per 100 sorties. Britain was fighting half-blind. The problem wasn't desire, it was physics. Chain Home's radar operated on wavelengths measured in meters, requiring aerials taller than a house and transmitters that consumed enough electricity to power a small village. Engineers at Bordsey Research Station had calculated the grim arithmetic. To detect an aircraft at 10 miles, a radar set needed to transmit thousands of watts of radio energy. The valves capable of generating such power weighed hundreds of pounds and produced ferocious heat. Even if you somehow crammed the equipment behind a pilot's seat, the aerials would create so much drag that the fighter would barely reach 200 miles per hour. Squadron leaders dismissed the notion entirely. What good was a radar-equipped fighter that flew slower than the bombers it was meant to intercept? The Air Ministry established a specification nonetheless. They wanted airborne interception equipment, AI for short, that could fit inside a Blenheim or Beaufighter, detect targets at several miles range, and weigh less than 500 pounds complete. Physicists responded with designs that filled entire notebooks with calculations. They proposed shorter wavelengths, which would permit smaller aerials, but the radio valves of 1939 simply couldn't generate meaningful power at frequencies above a few hundred megacycles. Laboratory experiments produced depressing results. A transmitter operating at half-meter wavelengths might produce 10 watts, barely enough to light a torch bulb, let alone bounce a detectable signal off a distant aircraft. Britain's predicament was shared by every nation pursuing military radar. German scientists faced identical constraints. American researchers at the Naval Research Laboratory struggled with the same valve limitations. French engineers working at the Magnetron laboratory in Paris before the fall had explored numerous blind alleys. The consensus held that airborne radar would require a fundamental breakthrough in radio frequency generation, something that existing thermionic valve technology simply could not deliver. The laws of physics appeared immovable. Inside a conventional valve, electrons streamed from a heated cathode towards an anode, with intervening grids controlling the flow. At high frequencies, the distance electrons traveled became comparable to the wavelength itself, causing the valve to stop functioning as an amplifier. Transit time effects destroyed efficiency precisely when power was needed most, yet the Luftwaffe kept coming, and British cities kept burning. Something had to change. John Randall and Harry Boot arrived at Birmingham University's physics department in February 1940 with a problem that had defeated everyone else. The two men made an unlikely pair. Randall, 34, was a spectroscopist. who studied how atoms absorbed light, whilst Boot, 27, had spent his doctorate investigating the behavior of electrons in magnetic fields. Neither was a radio engineer, neither had designed valves for commercial use. Their professor, Mark Oliphant, had received an urgent request from the Air Ministry's Scientific Liaison Office. Britain needed a device capable of generating high power at wavelengths around 10 centimeters. Could Birmingham contribute anything useful? Oliphant handed the challenge to his two least experienced researchers, reasoning that fresh minds might see possibilities where experts saw only impossibilities. The magnetron already existed as a concept. American engineer Albert Hull had invented it at General Electric's laboratories back in 1921, creating a valve where electrons spiraled through magnetic fields rather than streaming in straight lines. Various researchers had tinkered with magnetron designs throughout the 1930s, but the devices remained laboratory curiosities producing modest power outputs. Randall and Boot spent a week reading through back issues of scientific journals, sketching ideas on the blackboard in their drafty laboratory. They recognized that the fundamental challenge was extracting energy from the electron stream efficiently. In a conventional valve, electrons did their work and then splattered uselessly against the anode, wasting most of their energy as heat. What if the electron cloud could be made to resonate, oscillating at microwave frequencies like a vibrating string? Boot proposed something that seemed absurd when he first drew it. Instead of a solid anode, he sketched a copper cylinder with 6 circular holes drilled into it at precise intervals. Each hole would act as a resonant cavity, a chamber where electromagnetic energy could slosh back and forth at extraordinarily high frequencies. The dimensions mattered critically. A cavity measuring roughly 1 centimeter across would resonate at 3,000 megacycles, corresponding to a wavelength of 10 centimeters. Place a cathode at the center, apply a powerful magnetic field perpendicular to the structure, and electrons would spiral outwards, passing the cavity openings and inducing oscillations. In theory, the resonant cavities would feed back into the electron stream, bunching the electrons into spokes that rotated around the cathode. Those rotating spokes would drive the cavities harder, which would bunch the electrons tighter, creating a self-reinforcing cycle that converted DC power into microwave energy with stunning efficiency. Randall calculated the expected performance. If their mathematics were correct, this cavity magnetron might generate 1,000 watts continuously at 10 centimeter wavelengths. The figure seemed preposterous. Existing klystron valves at the telecommunications research establishment could barely manage 10 watts. 100-fold improvement from a device they could machine in a university workshop. The equations insisted it was possible, but equations had been wrong before. They needed to build the thing and test it. The university's workshop technician, a man named Skinner, spent 3 weeks machining the first prototype from solid copper. The tolerances were demanding. Each cavity had to be positioned and sized with a precision of a few hundredths of an inch, or the resonances would fall out of synchronization. Skinner bored the cavities using a milling machine, creating 6 identical chambers, arranged symmetrically around the central cathode space. The cathode itself came from a scrapped radio valve, a tungsten filament that would spray electrons when heated. Randall designed a magnetic circuit using iron pole pieces and a permanent magnet salvaged from an old loudspeaker, producing a field of about 1,000 Gauss across the interaction space. They sealed the assembly inside a vacuum envelope, attached it to a high-voltage power supply, and placed a simple wire aerial near one of the cavities to extract whatever radio frequency energy might emerge. On the 21st of February 1940, they switched it on. The magnetron began oscillating immediately, generating so much microwave power that a neon lamp held near the aerial glowed brilliantly without any wired connection. Boot measured the output, 400 watts, continuous operation at precisely 10 centimeters wavelength. Randall telephoned Oliphant, who telephoned the Air Ministry. Within 48 hours, scientists from the Telecommunications Research Establishment were standing in the Birmingham laboratory, staring at the copper block that had just changed the war. The scientists from Telecommunications Research Establishment arrived expecting to find a mistake. Edward George Bowen, who had pioneered Britain's first airborne radar experiments, examined the cavity magnetron with the skepticism of a man who had spent years coaxing feeble signals from temperamental equipment. He asked Randall to repeat the demonstration. The neon lamp glowed again. Bowen requested a power measurement using calibrated instruments rather than Boot's improvised setup. The reading came back even higher. The magnetron was producing bursts exceeding 1 kilowatt. Bowen telephoned his superior, Robert Watson-Watt, the formidable Scottish physicist who had fathered British radar. Watson-Watt's response was blunt: check for experimental error, because those numbers violated everything the establishment understood about microwave generation. The problem was that the cavity magnetron shouldn't work, at least not according to the principles that governed conventional valve design. Every radio engineer in Britain had learned that efficient amplification required careful control of electron flow using grids, precisely shaped metal meshes positioned between cathode and anode. The grids acted like gates, modulating the electron stream in response to input signals. Textbooks published by Marconi, Standard Telephones, and the General Electric Company all emphasized this fundamental architecture. Yet Randall and Boot's device contained no grids whatsoever. Electrons simply spiraled outwards from the cathode, interacting with electromagnetic fields inside the cavities through what amounted to holes drilled in metal. To an engineer trained in established radio practice, this was rather like building a steam engine without pistons and expecting it to generate horsepower. Robert Watson-Watt visited Birmingham personally in early March. He was a man who trusted mathematics and mistrusted miracles, and the cavity magnetron struck him as suspiciously close to the latter. Watson-Watt understood resonant cavities from his pre-war work on shortwave communications, but using them as the primary element in a high-power oscillator seemed recklessly unconventional. Where was the feedback circuit? How did the device maintain frequency stability without a crystal-controlled oscillator? What prevented the electron stream from simply splattering uselessly against the anode structure? Randall walked him through the theory, the self-bunching effect, the synchronous energy transfer, the way cavity resonance locked the oscillation frequency with extraordinary precision. Watson-Watt nodded slowly, then asked the question that mattered most. Could they make it reliable enough for combat use? Military equipment faced demands that laboratory prototypes never encountered. A radar valve inside a Beaufighter would experience vibration from twin 1400 horsepower engines, temperature swings from -40 degrees at altitude to sweltering heat on Mediterranean airfields, and the constant threat of combat damage. The cavity magnetron's construction, a solid copper block with precisely machined cavities, actually offered advantages here. There were no fragile grids to shake loose, no delicate wire connections to fracture, no complex internal structures that might misalign. The whole assembly could be cast as a single piece if manufacturing techniques improved. Boot had already dropped the prototype from waist height onto the laboratory floor, producing only a slight frequency shift that retuning corrected. Watson-Watt requested 6 units for field trials. Birmingham's workshop wasn't equipped for production, so the Telecommunications Research Establishment arranged for the General Electric Company's Wembley laboratories to manufacture evaluation samples. Whitehall's reaction was less enthusiastic. The director of scientific research at the Air Ministry, a career civil servant named Henry Tizard, had built his reputation on careful, incremental advancement of proven technologies. Tizard appreciated the Magnetron's performance, but worried about committing resources to a device that might prove unreliable in squadron service. Britain was already manufacturing chain-home transmitters, AI Mark IV radar sets for night fighters, and ASV equipment for coastal command. The production lines were stabilized, the maintenance procedures were documented, and air crews were trained. Introducing a radically different technology mid-war risked disruption precisely when operational effectiveness was improving. Tizard's caution was understandable. The RAF had wasted considerable effort on promising technologies that failed under field conditions. The automatic gun-laying turret, the Prince of Wales's fire control system, and several classified radio navigation aids had all consumed resources without delivering proportional benefits. Yet the Magnetron's raw performance kept overcoming objections. By May 1940, the General Electric Company had delivered 12 units, and TRE engineers had built them into experimental AI radar sets. Flight tests from RAF Worth Matravers demonstrated detection ranges exceeding 4 miles, double what the meter-wave AI Mark IV could achieve. The 10-centimeter wavelength permitted aerials barely 2 feet across, eliminating the drag penalties that plagued earlier installations. Most remarkably, the Magnetron's reliability exceeded expectations. Units ran continuously for 50 hours without failure, far longer than the fragile klystron valves they replaced. Henry Tizard stood on the tarmac at Heston Aerodrome on the 29th of August, 1940, supervising the loading of a single metal trunk that contained Britain's most closely guarded secrets. The cavity Magnetron sat inside, wrapped in felt and nestled among technical drawings, performance specifications, and a working prototype of the AI Mark VII radar. Accompanying it were details of Britain's explosive research, proximity fuse designs, and Frank Whittle's jet engine plans. The entire package represented perhaps 5 years of German research effort. Tizard was about to hand it to the Americans with no guarantee they would reciprocate or even believe what they were being shown. Churchill had authorized the mission personally. Britain was fighting alone, and if the island fell, this technology would perish with it. Better to share it with a potential ally than let it die in the rubble of a bombed laboratory. The delegation Tizard assembled read like a directory of Britain's scientific elite. John Cockcroft, who had split the atom at Cambridge's Cavendish Laboratory, would explain nuclear physics research. Edward Bowen carried the radar equipment and enough practical knowledge to set up working demonstrations. Ralph Fowler brought intelligence assessments of German capabilities. The group would travel aboard a flying boat to Canada, then proceed by rail to Washington, where the American military establishment awaited with profound skepticism. The United States had maintained strict neutrality, and many senior officers regarded Britain's situation as hopeless. Why invest resources helping an ally that might surrender within months? Tizard's task was to prove that British science offered technologies worth America's industrial might. They arrived in Washington on the 6th of September. The initial meetings were polite but frosty.